All right, for this lesson, we're talking about rational functions and their graphs. And before we get started here, let's just recall what we learned last section. So in the last lesson, we talked about the parent rational function, which is y equals 1 over x. We have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. Remember, this is your x equals 0 line on the y-axis, and this is your y equals 0 line on the x-axis. So this is the parent function. For simple rational functions, such as these two, determining transformations in asymptotes is straightforward, right? The number on the bottom tells us to shift left or right. The number to the right tells us we have an upshift or a downshift. The number on top is our a, and if it's negative, we have an x-axis reflection. So this we can easily pull them from. But for rational functions such as this, determining transformations, specifically asymptotes, requires some work, right? So just to remind you, the asymptote here, the vertical asymptote would be x equals 6. The horizontal asymptote would be y equals 2. For this one, it would be x equals 0 and y equals 2 for the horizontal. We can't just pull those out for this one on the bottom, this example. We can't pull them out. We have to do some work to determine what the horizontal and vertical asymptotes are. So recall, the domain of a function is the inputs, or x values, which can be plugged into a function. The range of a function is the output, or y values, which are the results of plugging in the values of the domain. So just a note here, any x value that cannot be plugged in to a function is called a restriction. Okay, remember we have restrictions on the denominator. If it's 1 over x, we can't make x equal 0 because that would make a 0 on the denominator, and that would be called a restriction in that example. So we're going to go over a few. So for example, if we have y equals 1 over x minus 2, what x value cannot be plugged in here? Well, if I graph this, don't I have a vertical asymptote at x equals 2? X minus 2 here. This tells us that we're going to shift right 2, if you look at your notes from last time. And so this would also be where we have our vertical asymptote at x equals 2. Okay, so x equals 2 is a vertical asymptote because it is a restriction of the domain. If I plug 2 into here, 2 minus 2 is 0, and the denominator equals 0, and we can't have that. So whatever makes the denominator equal 0 is called a restriction. X equals 2 cannot be evaluated for y equals x minus 2. Okay, so a note here is vertical asymptotes. Remember, this is a vertical asymptote, one that points up and down. It's an x equals. Vertical asymptotes impact domain. Remember, domain is talking about the x values. So for the next couple slides here, we're going to talk about vertical asymptotes. So the domain of this function, the domain of y equals 1 over x minus 2, which is what we just graphed up here, is all real numbers except x cannot be 2. Because if we plug 2 into here, it equals 0, and we can't have a 0 on the denominator. Also, that's where our vertical asymptote is, right? All right, so to determine any restriction on the domain of a rational function, set the denominator equal to 0. That's how you figure out where your restrictions, I think I said restrictions, that's how you determine where your restrictions of the domain are, okay? So here's the example. Example 1, we're going to determine any restrictions of the domain. Y equals 4x over x plus 7. So remember, we just set the denominator equal to 0, and we solve for x. That means x equals negative 7 is a restriction. Because if we set negative 7 back in for x, that makes a 0, and we can't have a 0 on the denominator. So, likewise, let's set x squared plus 6x minus 16 equal to 0. We have to factor that. So it's x minus 2 times x plus 8 equals 0, and then we set each of these equal to 0. So x minus 2 equals 0, or x plus 8 equals 0. and then we solve for x on each one. That means x equals 2 is a restriction, and x equals -8 is also a restriction. Looking at number 3, we're going to set the denominator equal to 0. Again, we have to factor that. So x plus 7 times x plus 3 is the factored form. And we're going to set that equal to 0. And we're going to split each one off. So x plus 7 equals 0 and x plus 3 equals 0. So x equals -7 and x equals -3, and both of those are restrictions. Again, this just means that if you plug in a -7 to x here, if you plug in a -3 to x here, it's going to make the denominator equal to 0. And same thing here with 2 and with -8. So talking about restrictions, there are two types of restrictions of a domain. We have either removable discontinuities or non-removable discontinuities. Those are the two types of restrictions of a domain. Okay, so removable discontinuities are restrictions that can be removed by simplifying or factoring the rational function. Non-removable discontinuities are restrictions that are not removed by simplifying. So here, graphically, when we're talking about removable discontinuities, graphically the function has a hole in the graph. And with non-removable discontinuities, graphically the function has a vertical asymptote. Okay? So if we're looking at a vertical asymptote here, we're looking at a non-removable discontinuity. And we'll talk about holes in a different lesson. We'll go more into that as well. Okay, so this is what we mean by factoring and then having it be removed and not removed. So let's talk about this on the next page. Determine and classify restrictions of the domain. Okay, so remember, here we have to factor. So we have to factor the bottom. X squared minus 4x minus 12. This is the factored form. Okay? So the restrictions, remember, we set it equal to 0. So we're setting the bottom equal to 0 still. We just kind of jumped from one step to the next. So this is really saying x squared minus 4x minus 12 equals 0. Then we factored both of these into this. We set each equal to 0, and x equals 6, x equals -2. Okay? So those are the restrictions. X equals 6, x equals -2. Now, x equals 6 is non-removable, but x equals -2 is removable. So here's the simplified version. Y equals 1 over x minus 6. Now, why is this called removable? Because look, we can cancel out x plus 2 over x plus 2. I can cancel those out. When we factored the denominator, we can cancel x plus 2 and x plus 2, and we're just left with 1 over x minus 6. Meaning that the x equals -2 is a removable discontinuity, and the x equals 6 is non-removable because we don't cancel that one out. And this is your simplified version. All right, factored here. So on the top, remember, if we have 3 terms, we're going to look for GCF first, but then we're going to put it into the factored form like this by looking for a times c and then adding up to b. For the top here, we always want to look for GCF first, and then we can do difference of squares, or we can even do sum or difference of cubes. So those are the things we look for when we have 2 terms. So when we have 2 terms, we first look for a GCF. So let's take the GCF. We actually have a GCF on both the top and bottom. So we can take out an x on the top and an x on the bottom. So on the top, we're left with x plus 4. When we take out a GCF of x, we take out a GCF of x on the bottom, we're left with x squared minus 25. Now look inside the parentheses. I can't do anything else with x plus 4, but x squared minus 25 is a difference of squares, which means we can go further with this. We can actually turn that into x plus 5 and x minus 5. All right, so this is our simplified form. X squared minus 25 turns into x plus 5 and x minus 5. Our restrictions, remember we set the denominator equal to 0. So x equals 0, x equals 5, is when we set this one equal to 0, and x equals negative 5 when we set this one equal to 0 and solve for x. So we have 3 restrictions here. The first 2 are non-removable, so x plus 5, x minus 5, we can't cancel those out. X equals 0, we can cancel that out with the x on the top. So this is called a removable discontinuity. And here's your simplified version. Number 3, let's factor out the denominator. So x plus 5 times x plus 4. We have 2 different restrictions, x equals negative 5 and x equals negative 4. We can't simplify with the numerator, with the top, so both of them are non-removable. Oops, I went too fast. And there's no simplified version here. The reason there's no simplified version is because we can't cancel anything out. So this factored version is actually the simplified version as well. Okay. So that was just with vertical asymptotes. The horizontal asymptote restrictions. The horizontal asymptotes of a rational function depends on the degree of the numerator compared to the degree of the denominator. All right, so if the degree of the numerator is greater than the degree of the denominator, the horizontal asymptote does not exist. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is 0, y equals 0. If the degree of the numerator and denominator are equal, then the horizontal asymptote is at y equals the leading coefficient over the leading coefficient. So let's put all this together by looking at 4 examples here. It says to determine the horizontal asymptote if any. Okay, so first of all, we have to make sure they're in standard form, which it is. It goes from 2 to 1 to no x's, 4 to 1 to none. Okay, so we want to make sure that the degree is at the beginning here. So the greatest degree, the 2 and the 4. So the 2, the numerator, is smaller than the denominator. So if the numerator is smaller than the degree of the denominator, the horizontal asymptote is y equals 0. Okay, number 2. The degree of the numerator is equal to the degree of the denominator. So if they're equal, then the horizontal asymptote is at y equals the leading coefficient over the leading coefficient. So 3 over negative 7. Don't forget to put y equals. For number 3, the degree of the numerator is greater than the degree of the denominator, which means the horizontal asymptote does not exist. Now look at number 4. Number 4, there's an x to the 0 power on the top, right? Anything to the 0 power is 1. So the degree of the numerator here is smaller than the degree of the denominator, right? So if it was just this fraction, y would equal 0, but remember this is actually in that form where, remember, this is like the plus k at the end. So this is going to be your horizontal asymptote. Okay, so it's going to be at y equals 5 if it's in this form. If this was gone and there was no plus 5 and it just looked like that, your y would equal 0. The horizontal asymptote would be at y equals 0. But because we have that plus 5 at the end, it's going to be at y equals 5. Okay, so this is like the ones we talked about last time in the last lesson. All right, last page here. Determine horizontal asymptotes if any, state and classify restrictions of the domain, and write the rational and simplified form. Write the rational function in simplified form. So here we go. First of all, we have a horizontal asymptote at y equals 0. Why? Because the degree of the top is less than the degree of the denominator. So our horizontal asymptote is at y equals 0. That was the first thing. Determine horizontal asymptotes. State and classify restrictions of the domain. Okay, so we have to get it in factored form to figure out the restrictions, and also to write it in simplified form. If it just asked for the restrictions, remember we just set the bottom equal to 0 and we could figure that out. But when we're talking about the simplified form as well, and if we're talking about classifying the restrictions, not just stating them, but saying if they're removable or non-removable, we need to factor both the top and the bottom. Okay, so x squared minus 64, remember when we have two terms, we look for a GCF first. There's no GCF. Then we look for difference of squares, difference of cubes, sum of cubes. I see a difference of squares, so it's going to be x plus 8, x minus 8. And then on the denominator, here, let's look at this first step here. There's a GCF of x, so took that out first. And then we can actually factor x squared plus 12x plus 32 down more to x plus 8 and x plus 4. All right. Now, we have three different restrictions. We have x equals 0, x equals negative 8, and x equals negative 4. Let's state them as removable or non-removable. Remember, only the x equals negative 8 is removable because we can actually cancel these out. We can't cancel out the x equals negative 4 or x plus 4 term or the x. So both of these are called non-removable, and here's the simplified form. Okay, very last one. So for number 2, our horizontal asymptote is 1 over 1, which is just 1 because the degrees of the numerator and denominator are the same, so we take the leading coefficients in front. So 1 over 1, which is 1. We're going to take the factored form of the top and the bottom. Remember, this is two terms, so this is difference of squares. After we check for GCF, we see it's x plus 3 and x minus 3. And then the top is x minus 7 times the quantity of x plus 3. Can we cancel anything out? Yes. Oh, actually, let's look for the restrictions, and then we can simplify by canceling out x plus 3, which means that your x equals negative 3 is a removable discontinuity. And here is your simplified form.